In the past months, I researched how Cloud Code, Open Code, and Pi work under the hood. And now I want to teach you how to build your own coding agent harness from scratch. So by the end, you will understand how to take this harness and adapt it to your own AI application, and at the same time get that precious intuition on how to become a true power user of these coding AI agent tools. Enjoy. Okay, so this is what you're going to build. So we prepared a CLI application similar to what you're already used to, such as Cloud Code Codex, Pi, and so on and so forth. So basically, this will spin up a TUI, a interactive environment where you can just talk with your agent. This one is powered by Qwen 3.6, the 30.5 billion parameter model version, and we run it on Modal, right? So we chose a relatively small model to be able to run it on our own without costing too much. So we can actually see how we can serve our own model and power our own harness end to end, right? So now we can start chatting with it. We can say hi. You can see this progress bar. And next we can ask it like to list the directories from the current directory, some basic commands. Now it will ask us if it can actually execute this bash tool, which is super important to have guardrails in place, which we will learn to do later down the line. And based on that, for example, if you don't want to get these questions on any command, we also implemented multiple modes, mode edit, plan, bypass, basically to not ask anything. Basically, what we are already used to in harnesses such as Cloud Code. We also have skills. So for example, we prepared a couple of demos where you can very easily test this agent, or the good old grill me skill, right? And it also supports compaction and a lot more stuff. Basically, it supports all the features that a basic harness has in place, because the goal of this video is not to show you how the code works, but to show you how to actually build and design a coding harness similar to the code, right? And later on, you can take those skills and apply them in building your own harness. It doesn't really matter if it's a coding harness or any other type of harness in a different domain, because the reality is that the fundamentals are very similar. And even if you don't want to implement harness from scratch, just having a strong intuition on how those tools actually work under the hood will transform you into a real power user. So we can now just quit this application, and let me show you a couple of demos and what this agent is actually capable of. So as you've seen, we prepared these 6 demos, right? That are packed as skills directly into this repository. And a couple of them that I really like are the following. So for example, it can one-shot a snake game. Next, a more complicated example where it needs a bit more reasoning is to create a dashboard based on the statistics from a GitHub repository, such as Pydantic AI, where it needs first to gather all this data from GitHub and then render the HTML. And the most complicated example that we tested it with so far, because I plan to stress test it a bit more for future videos, is this, where it needs to create this visualization where you can see a knowledge graph out of a couple of sources, where basically it needs to plan multiple steps, where first it needs to scrape multiple articles. Then the LM itself needs to extract these knowledge graph triplets, save them to a file, and then create this HTML dashboard that can actually render that graph. Basically, it needs to go through multiple steps where each step is not that simple, right? And another demos that this agent is capable of is, for example, to find and fix a bug from a repository, to spawn multiple sub-agents into a repository and make a summary of it. And another interesting one, when we'll implement sandboxing from scratch, is to try to implement a feature only in a sandbox, where basically you ask what feature you want to implement, for example, a new CLI argument into the decode coding agent. And after it finishes that feature, it should create a pull request with a description for the pull request and ready for you to review it and merge it or ask it further for new improvements. Okay, so now let's actually see how this works, right? Because the scope of this video is to actually learn how to design this in the first place. And then in future videos from the series, I want to show you how to actually implement it, right? So we'll zoom in into each piece and learn how it actually works. Okay, so now let's start with the beginning, right? Which is the system design, the high level overview system design of the coding agent harness. Consists of 3 big pieces. we have the headless harness, which contains basically the agent loop plus all the features around it, which is then attached to two interface modes. The interactive interface mode, which is the TUI, which you just seen in action, and then a remote headless mode, where you can basically spin up this headless harness on multiple computers, basically do job, independent job in parallel, like a swarm of agents, right? And in this use case, you will see that you will need things such as a runtime, where you can actually have durability in case of something fails. After you look into it, you can just restart. Next, based on this, you will need like proper human in the loop. Because for example, if you run in parallel multiple agents and an agent decides to ask you a question, you don't want to completely block that resource, right? You need an async mechanism where while it waits for a response, it actually frees up those resources for other agents. And also you need replace and a bunch of stuff that you actually need in production to actually run this, which we'll see in future lessons. And for the interactive view, you need a way where you can basically just start asking questions constantly, right? So to do that, you need like a steering queue where you queue messages until they are injected into the agent loop. And in that case, whenever you type a new call or a new message, a new prompt for your coding agent, it doesn't interrupt the current agent loop, but it actually waits until the job is done. And then here inside the agent loop, we'll have just a standard agent loop, which is implemented into Pydantic AI, just to show you actually how much code you actually need into the harness relative to agent, right? Like this will create a clear separation between what's the agent loop and what's the harness. And ultimately, we will need to manage the LLM providers, the memory, skills, sandboxing, permission, an LSP server. This is a very interesting piece from the harness that's super important for coding agents, and compaction and so on and so forth. Okay, so let's start with a bottom-up approach in this use case, right? So the next element is the agent loop. Now, the bare bone coding agent loop is actually pretty simple, right? So as I said, we have this agent defined from Pydantic AI, where in reality, to create a coding agent, you just need to register a couple of core tools, such as the read, write, edit, and bash tools. Basically, with these tools, an agent can interact with your computer, right? It can read files, write files, edit files, and with Bash, it can basically do anything. It can run Python, TypeScript, it can compose any type of commands, and so on and so forth. So basically, with Bash, you unlock everything the agent needs to interact with your computer. But sometimes you want to help it out a bit, right? You want to put some grab and glob commands to actually make it explore repositories and files faster. You want to add, for example, a to-do write tool to help it plan more easily, right? So when it makes a plan, it puts that plan into a to-do list that it needs to execute. You want to give it, for example, access to the internet with web fetch and web search and so on and so forth. But remember, all of this is optional. For example, Pi, the coding harness, is shipped just with those 4 core tools, and it's one of the most popular coding harnesses out there. At some point inside the terminal benchmark leaderboard, it was around the 7th, competing with Cloud Code Codex and those big army knives from those billion-dollar companies, right? And again, relative to the number of tools that you're going to put inside your coding agent, this has a direct impact on your system prompt. Because usually a system prompt for the coding agent is very small, right? So we have here like 4 lines, and that's it, right? Because you want the system prompt to be as small as possible. Because in reality, a lot of this coding functionality is already baked into the weights of the LLM. So you don't need to be that explicit about what it needs to do, because those LLMs are already trained a lot on function calling, on how to interact with the computer, on code. They're trained on a lot of code. So they kind of know to do a lot of stuff on their own. And if you start to add more tools than those core tools, each tool, right, starts to pile up into the system prompt. And as you start to add more and more functionality, the system prompt starts to grow and grow bigger, which has a direct impact on your token usage, hence on your cost, and also on performance, because as you put more into that system prompt, it starts to confuse the agent. So you need to be really deliberate about what you actually put into the system prompt. And usually everything starts with what tools do you give to the agent. Now, on the harness side, there are around 6 models plus compaction. Here are the 6 modules, right? The core 6 modules that more or less every coding harness has. So the most obvious one are the LLM providers, right? So you need an LLM to actually power this thing. And we mostly use Modal here, Modal endpoints, where it's very easily to just spin up open source models such as Quen in your use case and just use them directly to the OpenAI protocol, but you can also very easily spin up through their serverless options, more powerful models such as Kimi K3 or GLM 5.2, right? So these really powerful open source models that are kind of on par with what Anthropic and OpenAI offer. But we chose a smaller model to actually show you that a smaller model can do a lot of stuff, right? And to actually run this on your own pretty cheaply, right? So with around $30, you can go through with Modal through the whole course end to end. And to actually show you how to support multiple providers, we also squeezed in Open Router, where you can run any other open source model through their API, and also Gemini to support a closed source solution as well. But remember, the idea of the harness is that ideally it's independent from the model. So that's why we squeezed in multiple LLM providers to show you how you can actually build this independent from the LLM. Next, we have sandboxing, which is probably the most important guardrail you can have out there, right? So where we implemented local sandboxing via Docker and remote sandboxing via Modal sandboxes. And the reality is that, yes, the LLM can, for example, very easily hijack a local Docker container, but I just want to show you how the foundations, the fundamentals on how you can actually run an agent into sandbox. And then if you want to switch to a different tool, that's pretty easily, right? And we will also implement permissions where you can put your agent into edit mode, plan mode, bypass mode, right? Where based on the mode, it asks you if it can run some tools or not. For example, in edit mode, it doesn't ask you if it needs permission to edit a tool, but it asks you for permission if it needs to run bash, right? Where bash usually is the most dangerous one. And also memory, right? Agents MD and memory MD file that loads and personalizes the coding agent, the skills, the LSP server, which helps the agent query for symbols within your code base and to actually get quick syntax feedback loops. Because the reality is that the feedback loop is the most important. If you create the right feedback loop into your coding agent, then it can get really fair. Even with smaller agents, those feedback loops basically guide the reasoning and the next step. And ultimately, compaction. We'll also have compaction. So basically, these 6 modules plus compaction are like the key elements that any coding harness needs. And optionally, you can also add like an MCP client into this mix if you need to talk to MCP servers. But in my opinion, that's optional because many times you don't really need an MCP server because, for example, through Bash, you can actually run, right? Through Bash, you can very easily run CLI commands to talk to external services. And now I want to talk more about LM providers and costs. So you might ask, on top of why these 3 LLM providers, why these exact 3 LLM providers? And they actually have a really good mix between build versus buy, which is ultimately always the concern for if you want to use them in companies, you always end up into this build versus buy scenario where you need to decide, right? And Gemini is completely buy, right? It's proprietary, you can use it as an API, and that's it. Next, Open Router is somewhere in the middle, right? So you can also use open weights, but as a service. So it's still buy, but at the same time, it's very easily to switch from from open weights hosted on Open Router to something hosted on your own without impacting performance at all, right? So that's why it's somewhere in the middle. And next we have Modal, where we serve the open weights on our own. So basically, we kind of own the infrastructure. So as I said, this is a mix of everything, but the end goal is always that the harness should be independent of the model, always, as much as possible. Yeah, it's true that, for example, harnesses such as Cloud Code, they're working probably better with their models because they're hyper optimized to work with their models. But if you go, once you go into a harness that is generic, you need to take this into consideration, right? So it's a similar discussion between Apple versus Android. Okay, so when it comes to cost, there are actually 2 scenarios that you need to consider. The first one is pay per token versus GPU time. And the second one is serverless versus reserved GPU time. Usually, most of us are actually stuck somewhere here, or you're using a subscription, right? Which is actually this pay per token structure kind of packaged into subscription. But in reality, you can also go and pay for GPU time, right? So for example, you reserve a machine and you just pay for the time that machine is reserved and not on how much you actually use it. And of course, in this use case, there are trade-offs, right? Let's take this example where we want to process 1000 docs, where let's assume that each document has on average around 30K tokens, which end up that in the scenario where we need to process 30 million tokens. Because you just want to process a bunch of models, we we assume that you don't want to go with Opus or Fable or the similar models from OpenAI, and probably Sonnet, something like Sonnet, is more than enough to process this data, which at the time I'm recording this video has $3, 1 million tokens as input, and $15 per 1 million, right? 1 million tokens as output. 1 million tokens for both input and output. Basically, if we crunch the numbers and if we put these 30 million input tokens and we assume that the output has around 50K tokens, these numbers, which ends up with $97, which is pretty expensive to process a bunch of documents, if you ask me, right? Now, if we go with the GPU type option, which, for example, we can very easily do with Modal, right? Because with Modal, you basically reserve GPU time. You pay per what you actually use. For example, we hosted Quen on a H200 GPU, which cost around $454 per hour. And the thing is that Model is serverless, so you just pay as you use. And once this goes idle, the GPU goes down, so you don't pay anymore for it. But the idea is the same. You pay per GPU time, not per token. In this use case, we have to frame the problem differently. We need to frame it on how many tokens we can process per second. So let's assume that our throughput, right, is around 3K. And if we crunch the numbers, then we can process these 30 million tokens in around 3 hours of GPU time, which end up only to $13, right? So there's a huge difference between $97 and $13. Now, the thing is that in reality, the numbers are not that ideal, because if you have bugs in your code, and for example, while you process this with Model, the agent for some reason decides to hang, right? It decides to ask you a particular question. It decides to stop, and you don't properly handle to actually turn down your GPUs and scale down when there's no work to be done there, and all those scenarios and use cases that you need to be careful about. These numbers, these 3 hours numbers, can very easily go up, and your costs go up with them. So basically, if you pay per token, it's a lot more predictable. Everything is a lot more predictable, even if it's more expensive. But as you go on the reserved pay per GPU time, everything becomes, you have more control, you can reduce costs, but at the same time, you can have bugs that can increase your costs very easily. Now, the second dimension relative to the GPU time issue, for example, Model is on the serverless side of things. While on the reserved GPU time, you can go with Rampod, GCP, AWS, or whatever cloud provider, where you basically just reserve a number of GPUs 24/7 for, I know, a couple of months, years, to actually run your workload. And the thing is that when you do that, you usually need to reserve your peak demand, because you cannot scale up, right? So you need to have available all the GPUs in place to actually handle your peak demand. And in reality, so this is what happens for reserved GPU time. And for example, for serverless, you actually pay for the average demand, because serverless scales up and down whenever, for example, on a spike, you just scale up whatever and handle all the traffic that you need, and then you scale down and you don't pay for what you don't use. So basically, you don't reserve the infrastructure. On the serverless side of things, they just handle whatever they need to handle. Another thing is that for serverless, you usually pay more per hour than for reserve. And that's why at the beginning, reserving a GPU might seem a lot cheaper. And sometimes it might be, right? So I'm not saying that one is good and one is bad. I'm just giving you this math to actually understand the difference between the two. Here, basically, how you can think of it. So we have this final formula that kind of decides and shows you the difference between the two. So this one is also here, so you can understand it more easily. And for example, let's take the example where the price for the reserved is 5 times smaller than the price for the serverless, right? And the demand that you need for reserve is 5 times higher than what you need for serverless, because your peak, right? Your peak requirements are 5 times higher than the average. In that case, in this particular case, where the difference between the price and what compute you need is kind of similar, you basically end up with the same price ratio between serverless and actually reserving. This is like the baseline. Now, if the demand between the two, between the reserved and the serverless, is a lot higher, right? Your peak is, for example, 40 here, then you actually pay a lot more than you would with the serverless option. And if the difference in price, for example, is a lot smaller relative to reserving, for example, if the difference in price here will be 50, then reserving is actually cheaper. So you have basically these two knobs that you have to think about. Enough with the pricing. Let's go back to the actual architecture and see how we can build the harness. Okay, so as you've seen in the beginning, we have two modes, the interactive mode and the remote mode. So now let's zoom in a bit more into both, right? So the interactive mode basically has this a TUI where you can just chat within the terminal with the agent and do your own thing, similar to all the tools, the coding agent tools out there. To be honest, to me, the most interesting part on top of the UI, like I'm not a UI guy, so the UI is not that interesting to me, is the steering queue that basically makes the connection between the TUI and the agent loop especially. So basically when you're inside the TUI and you start typing messages and start talking to the agent, the reality is that you cannot directly send those messages inside the agent loop because then that message will just basically hijack the model call and corrupt your loop, right? So what you need to do is actually put them in a queue, in a buffer, and wait for the agent loop to get into a state that where you can actually append your new message into the agent loop. And a few very common states where you can start and altering the state of the loop is after a to call is finished, right? So your to call finished, it appends to the state, to the message list, to the context window. It appends the output of the tool. And then you can also start appending your new message, which goes inside the next model call. And then the model actually picks up on your next loop. And another option that you can do is actually to wait for the whole loop to finish relative to your first goal that started from here and just append your new goal when the loop finishes, right? And basically this steering queue and this priority gate, with priority gate is more like a virtual concept. It doesn't actually exist into the code, is to decide when it can take new messages and inject them into the agent loop. Now, if you go into the remote mode, we'll do that via Kitaru, which is a runtime used basically to run agents in headless mode. Some use cases are like running remote agents into the cloud, or for example, evals for eval harnesses, where they have this replay feature where, for example, you can inject your traces from your observability tool, such as Opik. You can inject them into Kitaru, and then it, because it uses durability, where it caches the checkpoints within your agent. For example, each model call, each tool call is a checkpoint. You can start replaying and branching from each checkpoint. Okay, so for example, what you can actually do here with replays. Let's assume that you have a model call, a tool call, a model call, two tool calls, and a model call. A pretty basic like agent loop scenario. And then with replays, you can say that, what if I alter the state of the LLM from this part? So you can start doing something like this. Let's say that we want to change the model type, right? A very basic thing, but you can basically change anything about that model call. And then you want to see what happens starting this point. What you call only a tool? What you call three tools? So you can basically test and evaluate the agent starting from this checkpoint, right? Basically, they share the state up to this point, and only up from here is different. And this is incredibly powerful during evals, right? So basically, you can explore all kinds of possibilities and see if you do that tweak, if you do small tweaks to different timestamps, how does that impact your application? And basically, Kitaru comes with this dashboard where you can see all your runs, and it provides via code all these capabilities. And as I said in the beginning, it also comes with the human in the loop capabilities, where if you run remote agents and one agent halts, it doesn't stop your entire it doesn't block your compute. Basically, it frees your compute and lets another agent use it, and after the human inputs whatever needs to input, uh it starts taking the compute back and continue the work. And we'll have a whole lesson just on this, just so you know, so I won't dig more into it at the moment. But now I want to explain more on the architecture side how this looks like. So we basically have the runtime split, where Kitaru is like the control plane, right? So the work doesn't actually go inside Kitaru. Kitaru just takes care of orchestrating the whole thing. And next we have execution, right? Where the agent, the headless harness in this use case actually runs. And we will run it on Modal because it's easy. There's actually a third element to this, where you run the sandbox, right? So execution and sandboxing are actually two different environments because the sandbox needs to be a different environment than where the agent itself runs, right? So for example, here inside the execution, we will run the model, and into the sandbox, we can run the tools. But the reality is that these two communicate with each other. And this is what happens if you have sandboxing in place, or if you don't have sandboxing in place, then you run everything in here within the execution environment. But again, we'll have a lesson just on sandboxing where we'll explain this in more depth, but this is like the architecture, the deployment architecture that you need. And you also need to deploy Kitaru somewhere, and we will deploy it on GCP via their open source Docker image. So we will also see how we can actually ship this whole thing via a bunch of CLI and shell scripts that we implemented. And the last thing that I want to actually talk about when it comes to interfaces is why do we need to separate that remote mode from the interactive mode, and why don't we actually add more modes, right? And the reality is that you can, but I just wanted for this educative purpose to keep it simple, let's say, as simple as possible. And in reality, for example, you can add a message bus between your headless harness and all the interfaces that you want to implement, such an interface for the ID, for WhatsApp, for Slack, for web, or whatever where you want to chat with your agent. And for example, you can add a message bus between the two that kind of keeps the state between the interfaces and the headless harness. And what happens here is that when a message goes into your headless harness, then the message bus takes care of synchronizing that interface with the other interfaces. We won't implement this, but for example, open code, the open source harness, they have this implemented over there, and this is how it works in case you want to take a look. Okay, so the last piece of the puzzle is observability and AI evals. The thing is that usually you need to think about this after you wrap up your first iteration of your harness or any other AI application, not only after you're far down the line. For example, observability, where you can very easily, like a bare bone observability is where you can easily monitor threads, which usually are the conversations, the whole conversation from you with your agent, traces, which is usually one message. Like, so you send one goal to the agent and the whole loop until that agent actually goes through some tool calls, another model call, another tool call, and so on and so forth. That message and response turn as you as a user is a trace, basically one agent turn. And then you also have the spans where you can easily inspect one tool or LLM call. And the thing is that you usually need this in place since day zero, because as you can see here, this is a trace. You can very easily inspect everything that's going on, like every tool call, every LM call, the token count, the what model is running where, all the metadata. So you can very easily inspect what the heck is going on, right? Because from the terminal it is terrible, from the logs it's terrible to go through these traces. So we are using Opik here for this course, and it has like a very generous plan. You can very easily plug it in, and we recommend using this tool or any other observability tool since day zero. Even if you build your own, you need this as quick as possible in your development lifecycle. And the last layer is the AI eval harness, which is actually part of observability, right? They often come together. And again, we'll have a whole lesson on AI evals, but what we'll implement is three perspectives of this AI evals harness, because this AI evals harness is actually a whole different application on top of your coding harness, where the AI evals harness sits on top of the coding harness and basically evaluates it, you know. And we'll have three scenarios. The first one is internal benchmarks, which basically are used to ask, does it work as we expect it to work? Where basically you try to put a number on the performance of your system, right? And it's very important usually to have like an internal benchmark because you define performance, right? And it's super important because this will be used to optimize your features. So basically, every time you start a new feature or you want to improve a feature, this will be like your North Star. You know, you start running experiments, and basically what you want to do is improve the performance on those features by looking at those metrics. So this will always act as your North Star. And if your North Star is wrong, then you'll go into the wrong direction. So this is really important to be defined, right? And probably on your own application, not to something generic that you found on the internet. The second family of AI evals are usually about regression tests, right? So this is when you want to ask, does it still work? So let's say that you ship the feature and you need to improve it, you do some changes to it, or you do some changes to another feature. And the thing is that when you, for example, change the system prompt, change the description from a tool, or whatever you do, it can have an impact on your current feature or on other features. So you need a way to see that whenever you do changes to your code, it doesn't affect the capabilities of what you currently have, right? So basically, the name comes from standard software engineering regression test. It tests regressions, but you kind of need to implement them differently than standard regression test. And in reality, these two, the internal benchmark and the regression test, can have overlaps between the two, right? But they're kind of in the software development lifecycle, they have different purposes. And after you ship, right, your application actually runs in production, you want to ask yourself, does it keep working? And basically, does it keep working in production? Does it work as we expect to when it's actually shipped to users and is used by hundreds, thousands, millions of users? And that's where production evals kick in, and where you want to actually score production evals in real time. And again, in reality, you can actually leverage the same evals from here, but you run them at a different point within your application. And usually all of this is powered by your AI evals and observability layer, which I like to call it like your AI evals harness, as I said. And in this use case, we will use Opik as well for this, which allows us to like keep track of data sets, run experiments, keep track of test cases, and all everything that we need for this. And that's it. That's like the architecture of this coding harness. So we had what is capable of to actually build. We had the standard architecture and the agent loop. We had the modes in which you can interact with the harness, and then we have observability and AI evals. And in future lessons, as I said, we will start zooming in into all these elements and actually see how we can implement them and how they work in detail, right? We will understand the why we actually need them even more, the what they actually are in even more detail, and then how they actually work and how we can actually implement this. Okay, so if you want to try out the Decode Coding Agent, you can go into the Building a Coding Agent from Scratch course GitHub repository, and you can take it from here. You can clone it, fork it, try it out, build your own twist to it, read the code. You can do whatever you want with it, right? And that's the scope to actually learn and build something cool out of this. And we did our best to document everything that you need in this README on how to run it and play with it. And inside this video, I won't bore you with any documentation and step-by-step instructions, but I want to like quickly show you around what's inside there. So if you scroll down a bit more, where we have the outline of the whole course, right? Of the current lessons that we already shipped and what's coming next. And here you can see basically what you need to run each lesson. So basically here inside the install and usage part of it, we have here everything that you need to actually run like the prerequisites, the install, what you need to install, what environment variables you need to set up, how you can set them up, and basically, as I said, end-to-end instructions on how you can set everything up, basically. And next, inside the model endpoints section, here we have a special dedicated document on how we can actually spin up a model endpoint, such an endpoint that's using Qwen 3.6 on or other models, GLM 5.2, GPT OSS that has like 120 billion parameters, so it's a lot more chunkier. And we also propose what GPUs you need to run Edge. And as I said, you have here step-by-step instructions on how you can set everything up. So I won't walk you through into this video on how you can actually do it, because it's a bit time-consuming and boring, you know. But what I want to do here is to actually run a demo from a skill and understand what's going on into the agent loop by looking into the Opik observability tool, right? So actually to get the gist of what's going under hood. So if we go back into the ZID and we type code, we open up the TUI, and we can just type demo 6, the article knowledge graph 1, that basically scrapes a couple of articles, extracts a knowledge graph out of them, and renders that dashboard that I showed you in the beginning. We click enter, and then the agent kicks off, right? So now it starts to execute the plan that we have baked into this skill. So as you can see here inside the .decode skills, we have the standard skills protocol implemented, where inside the Demo 6 article knowledge graph, we basically have a normal skill with the name and description and the steps it needs to execute, right? So let me zoom out a bit here. So it's just like a normal skill that you will write for Claude or Codex and so on and so forth. And the output, the final output that we expect is a knowledge graph HTML file that contains the dashboard, right? And now I already ran this. The reality is that this will take around 10 minutes. And as you can see now, it extracts the actual knowledge graph from the articles. And the reality is that because it's quite a small model, like right, a 35 billion parameter model relative to what we would normally use from Claude or Anthropic, the reality is that because of this, it doesn't necessarily remember to follow the whole plan. That's what I saw. Sometimes it does, but sometimes it doesn't. So what I need to do is when it stops at some point, I need to remember him that, hey, continue doing this by following, for example, step 3 to actually write the graph JSON file, or with step 4, hey, have you actually rendered the HTML, and so on and so forth. Okay, as you can see now, it basically wrote the JSON file that contains the graph, and now it needs to verify it and output create the HTML file. But this can again take a bit, and what I want to do now is actually, I already ran this, and what I want to do now is actually show you the output, which you should expect here in the code output, right? I just instructed it to output everything over here, and just need to open it inside the browser, and you will have something like this, right? So you have basically concepts, tools, patterns, and problems, and you basically inspect each node. You can start dragging them. You can see the relationships between them and so on and so forth. And the thing is that you won't get 100% a one-on-one reflection of this because I haven't hard-coded this into the skill, right? I haven't hard-coded all the colors it should use, or how it should write this HTML with this dashboard and everything. I hard-coded only the bigger plan, and it's the agent that takes this decision. So you will most probably get a dashboard with a knowledge graph, but it would look different. And the last piece that I want to show you is how does this look inside Opik dashboard. So here inside the project, I have a bunch of projects, and I'll go into the decode local one. We also have the production one that we'll touch later on. And inside the logs, we have threads, traces, and spans. And what we are interested in are the traces. So here I have tagged a few as examples, and we can see, for example, that the duration, the input, total tokens that were used while running these traces. And let's open one. Here we can see it contains 21 spans. So basically this is an agent run, right? Since we inputted this plan via the skill, what went within the agent loop to actually execute this plan? So for example, we had a first chat turn that has multiple agent turns, where an agent run basically has a model call with the tools that it needs to run, right? So for example, the first tool run has created this plan, right? So it created that to-do list with 6 steps, where the first one is in progress. Now, here we can see, for example, that the first step was executed. We can see here like the output from the model. And for example, the output from the model, it's set to the hardness that it needs to call this to-do write tool with the state it needs to override. And here we actually call this tool. And what's interesting, for example, here is that ended up with an error, right? Where we need an approval from the user. And here we can see that it ran again after the approval, and then the model continuing processing it. And for example, here it started to fetch the articles containing the data. And here, after it fetched the articles, we can see that it started to update the plan, and ultimately in the next step, where basically it fetched the articles, updated the plan, we can see that it extracted the graph based on the crawled articles. And based on what I said you earlier, that's why I chose this example to see that it's not yet perfect, and why you need an observability tool is that for some reason it stopped following the plan here, and after it outputted, it extracted the knowledge graph, it stopped. It decided that, okay, I'm done. But it's not done, right? And that's why in another thread, because once the agent decides that it stops, it basically, the request response turn, it stops. So a trace, it's over. So next we need to go into the next trace, where basically I ask it, is the knowledge graph saved and the HTML rendered? And it realized that, hey, I'm not actually done. I need to kick off another agent loop, and I need to pick it up from there, right? For example, inside this tool call, it basically outputs the knowledge graph into the graph.json file. Now, the thing is that you cannot really learn how a harness for a coding agent works without sweating a bit. So I encourage you to clone the repository, set it up, and try it out. If you really don't want to, that's not an issue. You can follow along into the next videos from this series. Also, if you have any questions, you can leave them as issues into the GitHub repository of this course. And otherwise, thank you for your time and thank you for watching.